that second equation when x is equal to x of I. Now, would you guys not agree that the height of this ith approximating rectangle is nothing more than the difference of the output of these two functions when the input is x of I? And I think the horizontal width is just a small change in the x direction. Now, when I revolve this rectangle about the x-axis, shoot, I don't get a disk. I get really what's a
washer.
I'll call this the washer technique. And I think the volume is computed by looking at the limit of the Riemann sum of the volumes of all the washers, like I haven't read if I rotate about the x-axis. And I think the volume is going to be interpreted as nothing more than the outer disk minus the volume of the inner disk.
There's no pi?
What's that?
There's no pi?
There is now. And by the way, I can rewrite this as a single integral, getting the difference of those two outputs. Because my bounds are the same, I'm left with the integral from a to b times the difference in these two squares. And I'm integrating, of course, with respect to the variable x. And that's the formula I'm going to use. That's what's in my back pocket to compute the volume of solid revolution using the second technique, namely the washer technique. Let's give it a shot. Yeah, it's a very sloppy dx, isn't it? Well, if I'm going to rotate about that line y equals -2, let's play. In my picture, let me consider a vertical red rectangle, which I will now rotate about that horizontal axis. If I rotate about this horizontal axis at the line y equals -2, am I not going to get this as a mirror image?
Yep.
And therefore, won't I get this as the image of the corresponding washer in 3 space?
He said you can't draw.
Oh, I can't. Trust me. And I think to identify these functions' outputs, they're radii. Think about it, you guys. Watch. Look at this f of x of I. Isn't that the radius of the outer disk? And the g of x of I, isn't that the radius of the inner disk? So when I use this nifty little formula over here, I literally think of this is the outer radius, this is the inner radius. So is my black pen. If I can erase this, let's get started. I think the volume is going to be computed by looking at pi times the integral from one x extreme to the other again. That doesn't change. But I do think I've got the outer radius squared minus the inner radius squared. And I'm going to integrate respect to x. But that gives me pi times the integral from 0 to 4 of a difference, integrating respect to x, of the outer radius squared minus the inner radius squared. Now I want to impress upon you how lazy I am. I truly am lazy in this fashion. Can I label? And I'll label again. Now when it comes to this outer circle, which is the boundary of this disk, or excuse me, the boundary of the washer on the outside, would you guys not agree, this radius right here, the outer radius, isn't that going to be computed just by looking at this large y value minus a small y value on the vertical axis? This is an arithmetic question. Don't do any work. I think this distance here, which is the outer radius, is going to be a high y value minus a low y value. And don't you guys agree the high y value is just y sub I? The low y value is simply going to be, I don't know, no matter where this rectangle is, what's the inner radius? Say it again.
-2.
Well, I think I misspoke. Don't answer that question. I meant to ask, what's its position on the vertical axis?
-2.
-2. I'll subtract negative 2 from y sub I. And I think I get the outer radius as y sub I plus 2. I'll put it in. What did I just say? It was y sub I plus 2? I don't like it. I don't like it because I don't like having a y sub I put in here because I'm integrating with respect to x. Give me another name for y. I asked, give me another name for y. X to the 3 halves. Now, as far as the inner radius is concerned, look at my picture. Watch. No matter where this rectangle is, what's the inner radius of the circle? The difference in the y values. Large y value of 0. Minus a low y value of
2.
negative 2. And so I think the inner radius is simply going to be top positive 2 no matter where that vertical rectangle is placed, horizontally speaking. Well, look at that. I just set myself up a nifty little integral, and I can use that to value the volume of the solid of revolution. And I think what that in the end gives me is nothing more than pi times the integral from 0 to 4 of, I don't know, can you guys help me with this? I ask, can you help me with this? I know you can.
X squared plus 1 minus, oh no, x to the 3 plus 4.
Say it again.
Well, oh, yeah.
And then it generates nothing more than pi times 1/4 x to the 4th. I don't know. Is that a plus? Excuse my voice. Is that an 8/5 x to the 5 halves?
Yes.
Do you guys mind if I stop? Now it's just a numbers game, isn't it? I'd rather spend my time in class setting up these integrals. All right. Let's just graph these equations. What one? Which one?
They're both parabolas.
Yeah, I think they're both parabolas. Well,
Except one is half a parabola.
yeah, maybe I misspoke a little bit. This is just a half a parabola opening to the right. This is a full parabola opening up. Graphically speaking, however, don't you guys agree that the region bounded by those two graphs is sitting right here? So if I were to compute the volume of the solid of revolution by taking this two-dimensional region and rotating about the line x equals 2, ah, shoot, that's way over here. Unlike my previous examples, I think that gives me something quite different. And using my green pen, I'll draw not a vertical rectangle, but a horizontal rectangle. And that's what I'm going to rotate about the line x equals 2. Let's give it a shot. I'll call this point right here x sub I comma y sub I. I'll think of this point over here as x sub I bar comma y sub I bar. You guys, I'm making up this bar notation out of thin air. I don't care what you call them. Now, would you guys agree that rotating this beast about that vertical line x equals 2, the volume is going to be interpreted as nothing more than pi times the integral from I don't know where to I don't know where of the outer radius squared minus the inner radius squared. But this time I'm going to be integrating with respect to
Why?
Why? Because technically speaking, if I took the time and subdivided the interval from C to D on the vertical axis, then I think the vertical dimension of this rectangle is an infinitesimally small length in the vertical direction, a delta y. But yet again, when I take the limit of the Riemann sum, as delta y goes to 0, it's going to become a dy in the integrand's position. But we've got to be a little careful here, because I think when it comes to the outer radius, of an arbitrary ith washer that I've got positioned here, I think the outer radius, isn't it just going to be this big X value minus this small x value? And I think the big X value is constantly,
2.
I think the smaller X value is what I labeled as X of I. No, I admit, I've got to take this one step further, don't I? The equation of this curve right here really is this equation right here. And because I'm eventually going to integrate respect to y, don't you guys think I should rewrite the x of I in terms of y? But wouldn't that be the same thing as 2 minus y sub I squared? So I think another name for the outer radius is merely my 2 minus y squared. Oh, by the way, squaring it. I'll subtract from that the inner radius squared. So you guys, let me pull out a different color so I don't have to erase anything. I think of my pretty picture. Here's the inner radius squared. But I think that's the same as this large x value minus the smaller x value that I labeled x of I bar. But jeepers, the equation of this black curve, you guys, I didn't write it in here, but its equation clearly is this, isn't it? Well, relative to the equation, I think another name for x of I bar is going to be, I don't know, is that the square root of y sub I bar? Which means, back over here in the integrand's position, I guess another name for the inner radius is going to be 2 minus 1. Oh, by the way, it's being squared. And oh, by the way, I'm going to integrate with respect to the variable y. And thirdly, by the way, I don't have my bounds of integration. They range from y. That's the word one, not the letter y. Y. Because from here to here, I range from 0 to 1. No. It's really because from here to here, I range from 0 to 1. I know I end up getting the same bounds. Here's a lousy example. My point is, I really want to range in the y direction because I'm summing up the volume of the end washers. I'm rotating about the vertical line, x equals 2, when I got those horizontal rectangles. You guys with me? Give me some feedback. Is this so easy, it's boring you to death? Do you want to think about this, or is this just killing you?
It's easy.
Oh, get some stuff down.
So a little bit to think about.
Do some shells.
Somebody have a question?
So if
Yes.
the line you're rotating about is positive, no matter if it's x or y, it's always going to be 2, like the number minus a function.
Yes, it will. Now, the reason why I answer your question yes is because in my head I'm drawing pictures. Personally, I hate to memorize anything. I'm a mathematician. And if you have to memorize it, then go for it. I'm not trying to change your ways. Personally, I just think looking at the picture, you guys can just dump everything out of your mind. Don't think. And just look at the picture, you can determine which one's the front, which one's the back of the subtraction operation. I think. That's just the way I look at it. Do you guys think I can... Oh, I can't finish, can I? I didn't actually answer the question. Can I just take this one step further? Just one. Instead of 4 minus y to the 4th. No. I'm committing a horrendous math D mistake, aren't I? To expand this binomial square, I really end up with a 4 minus 4y squared plus y to the
4th.
Minus, let's do it again. Is that a 4 minus 4 root y plus y squared, plus y to the 1st?
Yes.
And then, I might need in here, excuse me, combine some like terms. Oh, not many, just the 4's cancel. Anti-differentiate term by term. And evaluate. Do you mind if I don't? That's the easy part, isn't it? Then do you guys think I could run amok? Can I finish up today's lecture by same picture, but rotating about the line y equals -1? Because my picture is so sloppy, can I regenerate it? And regenerating it. Horizontal x-axis, vertical y-axis. I've got this bounded region, again, same example, or at least same region in 2 space, I should say. A different example in the sense that now I want to rotate it about this line right here. But using the Washer method, I guess what I really have are these vertical rectangles that are gonna be revolved about the horizontal line at y equals -1. Let me label this point at the tip, x of I comma y sub I. This point down here as x of I bar comma y sub I bar. If I were to rotate this about, the line y equals -1, yes or no response? Would you guys agree? That this would be the value of the outer radius? I said value, I take that back. Pictorially, that would represent the radius of the outer portion of the washer. I just maintain in my lazy fashion, this is a vertical distance along the y-axis. Its distance is simply going to be computed this lazily. Its disposition on the vertical axis, namely y sub I, minus this position on the vertical axis, which is -1. And that being the case, I think the outer radius is merely the difference of those two beasts, the y sub I minus y -1. It's just that eventually I'm going to integrate with respect to what variable?
X.
X. That being the case, I think I got a little job to do. That job is to take this y sub I and rewrite it in terms of x sub I. But that's in the boundary of this curve that's got that negative concavity. Isn't that the graph of this equation? And therefore, I think in blue, rewriting y sub I plus 1 is as easy as rewriting as root x sub I plus 1. That's the outer radius. As far as the inner radius is concerned with my red pen, well, everybody, here's the inner radius. And I think this is likewise going to be nothing more than this really high y value that I called y sub I bar, minus low y value of -1. But here too, you guys, I'm panicking. I really want to generate an integral in terms of variable x, and I've got an expression in terms of y sub I bar. I give up, claim defeat, change things. In black, excuse me, equation that curve is this. So I think another name for my red y sub I bar is going to be nothing more than my red x sub I bar squared plus 1. Look at that. I got the inner radius. It's nothing more than x squared plus 1. Oh, but shoot, remember, I got to square it. Then remember, I got to look at their differences. Then I got to integrate with respect to the variable x. I got to multiply the result by pi. And I've got to make a determination of what those bounds of integration are. They don't change, do they? I'm stacking those vertical rectangles from the left direction, or left extreme of 0, to a positive extreme, or rightward extreme of +1, but I admit it's along a different axis. Or shall I say, I got a pi times this integral from here to here. I don't know what else is next. This. Ah, shoot, we're such math D experts. We can do this, can't we? Maybe combine those two constants. Anti-differentiate term by term. Using the power rule for anti-differentiation and numerically evaluating. Piece of cake or not?
Yes.
Good. I was hoping you'd say that. And if you guys don't like my technique, don't worry about it. When we come to class on Monday, I'll give you a whole new one for computing volumes as solids of revolution. It's called the
Shell method.
cylindrical shell method, yes.
Professor
Oh, man,
Balga,
I still didn't get right.
can I make an announcement about these videos?
Please, can you
All
make
right.
an announcement while I get the homework set up?
Yeah.
You guys, Bradley wants to say something.
All right.
All right, so for some of you guys that took Math 30 last semester with Professor Balgai, you might know I already do this, but I film each of these classes and I post them on the internet. So if it's helpful to anybody, you can just access my YouTube page and check out any of the lectures. And basically all you need to do is just search Brad Morton. My handwriting is horrible on the chalkboard. Just search Brad Morton on YouTube. There's two of us on YouTube. One is a golf guy. I'm the one that looks like a cartoon ghost. And yeah, you can access any of the videos for this class on YouTube if it helps.
Do you have a labeling method like the date or do you succeed?
Yes, I just label them based on what we cover. So if we cover like 6.1,
So you put
it'll just say Math 31 6.1. Yeah. I put the homework and quizzes and all that stuff up there too.
So do you guys mind, can I just